Hello, everyone. My name is Dale Bremer, and it's a pleasure to be here. The title of my talk is, Can Small Unmanned Aircraft Systems Be Used for Turf Management? I would like to acknowledge Dr. Dion Vander Merwe of the College of Veterinary Science at Kansas State University as the co-author of this talk. Although he can't be here today to help record this, without his help, none of what I show you today would have been possible. With Small Unmanned Aircraft Systems, abbreviated UAS, we've seen a rapid advancement in technology in recent years that has resulted in really affordability in using this technology. There are many uses for small unmanned aircraft systems, but what I want to focus on today is the precision crop mapping for farmers, which we believe can be utilized for turf grass management, although really little research has been done to date on using UAS and remote sensing technology for turf grass management. So its uses are largely unknown in turf grass, and that's what I'm going to talk about today. Just to kind of start off with, there are a few limitations and concerns that you should be aware of when using these UAS. And one is privacy, of course. And in turf, we have a lot of lawns in urban areas where you have neighbors that may not appreciate it if you're flying a UAS around or near their property. So just something to be aware of. And also the FAA, the regulations, they originally were supposed to integrate their rules for UAS into the US airspace by 2015. That didn't happen. And so it's believed that that could happen at any time, but just be aware that anytime you're flying a UAS, that the FAA does regulate their flight, and you should be aware of what those are when you are flying. And as far as actually collecting data and taking measurements of turf grass vegetation, there are several ways that we can do that, and I'm going to discuss them in the next slide. But just a couple things to keep in mind, that it does take some time to process the images. And when we are talking about really seriously mapping the surface of the turf vegetation, it requires quite a bit of interpretation. And I'll talk that the need for that will become evident more in a little bit. So what about uses for turf? Well, first, just the bird's eye view. Just taking a regular quadcopter UAS with a video camera and flying it over your turf, you can learn quite a bit just from that. There may be patterns in the turf, maybe a stressed area from drought or disease or who knows what, that may be visible from the air that you can't see from the ground. So that's just one thing to be aware of. But as far as vegetation stress mapping, that's the kind of the more scientific use of UAS. In this, we attempt to use remote sensing and UAS for detecting drought stress, but we can also look for a number of other types of stress in turf, such as traffic, weeds, disease, soil compaction, overwatering, invasive species, or a number of others. Our overall goal is to identify stressed areas before they become visible to the naked eye. And part of what I'm going to show you a little later in today's presentation is some work that was funded by the U.S. Gulf Association, and that's exactly what we are trying to do, is to identify areas of drought stress before they are visible to the naked eye. And of course, the reason for that is because if we can identify these stressed areas before they're visible, then hopefully we could alleviate the problem before it becomes more severe. We did fly a 9-hole golf course in northeastern Kansas, and this is about a 4-minute video. I'm only going to show you just less than a minute probably, because we just don't have time to show it all to you. I will give you the link if you want to go watch it later, but We flew this golf course with a fixed wing aircraft. It took about 25 minutes to map the whole golf course. We flew at about a height of 400 feet, and the resolution at that height was about 5.5 centimeters per pixel. So it's really a pretty good resolution, much better than what you get with satellite or even flying with a Cessna aircraft, which usually has to be at a higher altitude, 1,000 or 2,000 feet. So again, it's fairly complex to do this. You have to program your flight path in a software and upload it to an autopilot, and then the plane will fly the course, the whole golf course, in kind of a grid pattern. You may have seen that earlier. And then afterwards, we have to process the images, which is fairly complex. And I will discuss that just briefly later on. When we were finished, we took multiple images that were collected when we were flying over the course. I didn't really mention it, but as that plane was flying over the golf course, it was taking pictures. And when we were finished, we stitched all those images together in software, using software, and came up with this image of the golf course, which we call an Ortho Mosaic. And just a couple things about this. The camera was modified. It was actually a Canon S100, modified to collect or take pictures in the near infrared, which is normally not visible to the naked eye. And it also screened out some of the different wavebands in the visible. And the only ones that were allowed in this image were the blue and the green, and as I mentioned, the near infrared. So there's really 3 bands, which allow us to create a vegetation index map. And that's what this is. This one's called the Normalized Difference Vegetation Index. It's really a measure of biomass, how much biomass or vegetation is on the surface. Areas of green, as you can see from the scale here, indicates a high biomass. And when you see black, there's really no biomass. Blue and pink indicate significantly less biomass. Or in our case, we like to use this as a stress indicator. And oftentimes if you see the green, that indicates relatively low stress when you're looking at a particular area. And we'll zero in on a couple areas here in a minute. And if you see pink or blue, that may indicate there's more stress in that area. We are going to look at just a couple of fairways here that are enclosed in these boxes, one here in the center, and then one over here to the right. The first fairway, you notice there are some areas of pink and blue that indicate stressed areas. When we showed this to the superintendent, he knew exactly what that was. He said on that particular fairway, they had an infestation of Poa annua, or annual bluegrass, and they sprayed it out. And so what we're really looking at here is those areas of pink on the fairway and even in the rough are where the Poa annua died, and it's just basically thinner vegetation there. When you look at just the raw image of that, you can tell that there are areas of gray which indicate thinner vegetation. You can see some of the soil through the vegetation compared to the more red areas in this picture. And I should point out, the reason that the color on this is a little different is because the camera was modified. That near infrared band really influences the way these images look. But you can still get a pretty good idea where there's healthy vegetation or where there's weaker vegetation. Now, this is the fairway that was to the right of that previous image. And overall, when you look across this whole fairway, it looks pretty good. There are a couple areas over here to the right where you can see little bare patch in the middle, and that was just from the irrigation heads. But overall, when you just look at it with your naked eye, it looks pretty healthy turf. When we look at the vegetation index, first of all, I should just point out that these areas here that look like they're pretty bad, if you go back and look at the raw image, that's just shadows from the trees. So you always have to be aware of that. There may be some interference in these images. We have to make sure we know what we're looking at. But outside of the area of the shadows from the trees, you notice right here in the center of the fairway, there's an area of yellow, which indicates a weaker turf than other parts of the fairway that are green. And this is very preliminary data. We really didn't have time to investigate it much, but as I've showed this to golf course superintendents since taking this image, many of them believe that it's probably caused by the area where golf balls land after a golfer tees off. They tend to land kind of in this middle area of the fairway, and then the golfers come out and tee off again, or hit, not tee off, but hit from this area. And that could cause some weakening of the turf grass. And again, just keep in mind that one thing we want to do with this technology is to try and detect problems before they become visible. So this is just kind of a real life potential application of this, although again, we much more work needs to be done to really validate this. So I do want to take just a few minutes to show you some of the work that we've done at K-State on this presentation that was funded by this research that was funded by the U.S. Golf Association. And the objectives of this research was to evaluate the ability of using remote sensing and small unmanned aircraft systems to detect drought stress in turf grass. A second objective was to compare measurements between traditional handheld methods and small unmanned aircraft system techniques in detecting drought stress. This study ran from June 29th to August 31st last summer, so it was a 64-day study. It was conducted on creeping bent grass mown at fairway height, 5/8 of an inch in our case. These plots were under a Rainout Shelter, and this Rainout Shelter protects plots from precipitation. This is a picture of our Rainout Shelter. If you look to the lower right, the Rainout Shelter is basically a building that's on rails, and when it rains, it triggers this building to move over and cover the plots so that no rainfall can fall on it. Then in that way, we can apply exactly the amount of water that we want. We applied it by hand, as you can see at the lower left. And this is just an area of the kind of the plot area taken with one of our UAS of the creeping bent grass. This area off to the north of it is actually a different study. We had 6 irrigation treatments ranging from well-watered to severe deficit irrigation, 100% to 15%, down to 15% evapotranspiration replacement. Obviously 100%, the turf grass was receiving all the water that it used, and 15% it received only 15% of the water that it used. So that's a very severe deficit irrigation, but that's what we wanted. We wanted to get a gradient. The measurements were taken weekly with the UAS, and again, we used a modified Canon S100 digital camera that had filters for the near infrared and the green and blue bands. We used a DJI S800 EVO UAS. It was a hexacopter, and we flew it at 50 feet above ground level. And I might mention that the resolution is actually better the closer you get to the ground. So when you are flying at 50 feet above ground level, the resolution is about 0.5 centimeters per pixel on the picture. When you compare that, when you fly at 120 feet, it's about 1.5 centimeters per pixel. And when we were flying at 400 feet, then the resolution is about 5.5 centimeters per pixel. So oftentimes, if we are on a golf course, we may want to take a closer look at a particular area of the golf course, for example, the green, then we may take one of these hexacopters down and fly it over the green at a lower level and get a little better resolution, a little better look at the green. Further methods, we process the images that we took with the Canon S100 using software, several packages here. And as I mentioned earlier, the post-processing of the data is quite extensive using this method, but it's what's required to get the vegetation maps that we need to try and detect the drought stress. So we did use several vegetation, actually 8 vegetation indices, as well as looking at the turf surface within each of the 3 individual bands, including the near infrared, the green, and the blue bands, just to see if we could detect drought stress in any of those bands. We also took some other measurements, the soil moisture to a depth of 3 inches, visual quality, which was just basically looking at the graph and making a rating on how good it looked, which is a very traditional method in turf research. We also used DSLR cameras took photographs with a regular digital camera to run through software and estimate its percent green cover. And we used a handheld device, a Spectrum Field Scout CM1000, to get a measure of normalized difference vegetation index from the surface. For our results, when we look at volumetric soil water content, let me just set this up for you. At the bottom here, you can see the treatments ranging from 100% down to 15% ET replacement, and volumetric soil water content is on the y-axis. And the letters indicate basically differences, statistical differences. So if you see the same letter on 2 bars, that means statistically they're not different, they are the same. But if you see differences, different letters, then they are different statistically. So I want to point out that from 100 to 65%, there was a significant drop in soil moisture. And of course, you can see that after that, 50 down to 30 and 15, there was additional drop in soil moisture. Not surprising because they were receiving less water. But we know that what we want to know is, can we detect differences in the vegetation, knowing that there's less soil moisture in the 65% treatment? Can we also detect a change in the vegetation using our other methods? Visual quality, when just visually, when we looked at these plots and rated them, there were no differences really between the 108 and the 80 and the 65% treatments. So even after we know that there's less soil moisture at 65% than there is at 100%, visually, when we look at it, we couldn't really tell looking at it with the naked eye. After that, when we get down to 50% and 30% and 15%, the visual quality dropped off rapidly. And I don't have time to show you all the data from our handheld NDVI and from our taking pictures with the digital camera and measuring percentage green colors. But with those methods, we also could not detect any difference in the vegetation or the turf grass between 165% or 100% and 65% treatments. However, when we use the UAS, we were able to detect differences in the vegetation between 100% ET and 65% ET treatments. This is just using the near infrared band itself, which is very sensitive to water. When you look at the differences in the signatures between 100% and 65%, the 65% is statistically lower than the 100%. We also found there was one other vegetation index, the green-blue band, which also was able to detect differences in the 100% and 65% ET treatments. No other of the vegetation indices were able to detect differences. So all this really to say that we were able to detect some differences in vegetation before it was visible to the naked eye. This is just a map of, basically it's a vegetation map of our plot area in the near infrared band. So when you look at the 100% and the 80% ET treatments, those that were receiving more water, they're a lot more green. And of course, that tells you that there's more vegetation there and they are under less stress. But when you get down to the 30 and 15% and even the 50%, you can see there's more red and yellow indicating more stress. The 65%, it's a little harder to tell. You kind of can tell that there's a little more yellow in them. But again, what we were doing was we were counting the pixels and the colors on the pixels and statistically taking measurements. And that's where we could detect, using this near infrared band, that there was a difference, a decreased, vigor in the turf grass from 100% to 65%. So again, this just indicates that ultra-high resolution remote sensing with small unmanned aircraft systems has the potential to detect drought stress before it's visible to the human eye. And just very briefly, before my time runs out here, there are additional techniques that we have used a little, but we want to use more in the future starting this summer. Thermal cameras, which you can take a picture of the surface and get a measure of the temperature of the vegetation, could be very useful in turf management because a higher temperature indicates greater stress. If if turf grass is transpiring less, there's less cooling of the leaves, and so the temperature starts going up, indicating a stress. So on our plots, where the plots were receiving more water, the temperature was cooler. It was about 37 degrees here, compared to the plots that were receiving less water. The average surface temperature was 41 degrees. So that was about 4 degrees higher Celsius. But this was fairly early in the study. So later on, we would have seen even greater differences. We didn't take regular measurements using this technology. And another thing that we can do using this technology is 3D images. So again, I'm just going to show you just very briefly a clip. We flew Firekeeper Golf Course in eastern Kansas. And this we can actually create a 3D image using this technology. And I want to point out, don't pay attention to the trees. They actually look very beautiful when we were there, but we just don't have enough data to make complete images of them. Focus on the surface of the turf. You can see the depressions and the bunkers, which we can actually measure accurately, the volume of bunkers, the slopes. And so I think that there'll be use for this, although again, we're just starting to explore this. So if you are interested in looking at any of these videos in their entirety, or there are some additional videos, feel free to look at the following links at some of videos that Dion Vandermerwe has created on his YouTube channel. And I also have a couple that we took of the Kansas State Turf Research Center. We just didn't have time to show today. With that, I would like to thank Dr. Jim Robbins at the University of Arkansas for inviting me to present this to you today, and also the U.S. Golf Association and the Kansas Turfgrass Foundation for funding this research. So again, thank you very much. And I'm excited to see where UAS and turfgrass management are going to, what it's going to become in the future. Thank you. Bye.